In this video, we're going to look at an introduction to vectors. So if you see this image here, it looks like array, which starts at one end, goes forever on the other end, and that's a symbol that we have above the variable that we use to describe the vector. But a vector is actually a directed line segment. So let's take a look at what that means. Well, a vector is going to have a size, so a distance that we call the magnitude, and it's going to have a direction, which is the angle. So we could create a triangle here and look at the angle that this creates, and then find the distance like the hypotenuse. Now if we talk about a scalar is only going to have size. It's not going to have an angle or direction. So that could be distance time volume. Now, looking at our vector, we've got two ends of our vector. So for vector A here, our initial point is this point here, and we call this here a terminal point. Another name for that is our tail and head of our vector. Okay, so that's going to come into play a lot more when we start adding or subtracting vectors later in this video. Well, now we showed before that these both look like rays, but we said that they are a directed line segment, and a line segment ends, which is why we call these both points, even though there's an arrow there. So it's kind of a mix between a ray and a line segment. And so what's the difference? A ray is a directed line, so they both have direction, but a ray only has an initial point and extends forever. A vector also has an initial point, but it has a terminal point, so it ends. It's really a line segment with direction that looks like a ray. So let's look at a couple examples of vector versus scalar. So we've got 4 examples here. Let's say you're pulling a cart up a 30-degree incline with 100 pounds of force. Well, a scalar doesn't have direction, and we've got an angle here for our cart, so that would be considered a vector. Your height, that's just size. That's something we can measure, but there's no angle, so we call that just a scalar, because your height is the same no matter what angle you're at. Temperature of the room, again, that's there's no angle or direction there. Here, plane traveling due north at 325 miles per hour. Even though it doesn't give us a numeric value for any direction, when we're talking about a bearing here, in this case north, that does give us some direction, so that would be considered a vector. Another thing that we'll get to in another video a little more closely is the magnitude of a vector. That's what we call absolute value. As you can see, we've got the absolute value lines here. Sometimes you see the double lines around the vector. And that's a scalar quantity that's equal to its length. Well, we call 2 vectors equal if and only if they have the same magnitude and the same direction. So we've got this vector v here. You see we've got direction that we're going, and if we're just cloning this here and we put this vector anywhere else on our page, well, all of these vectors are going in the same direction, and even though their initial point, the tail of our vector, is not in the same spot, still has the same direction, and it has the same length or magnitude. So all of these vectors would be considered equal. A couple other relationships that we have between vectors here. Now we can't always assume certain size or direction when we see images, but in these cases we can. We see these two look like they're parallel and the same length, and they are in fact equal. We should have the the little vector symbol above our variables v and w. So vector v would equal vector w in this case because they both have the same magnitude and direction. In this case, they look like they're the same size or magnitude, but clearly different direction. In this case, again, they're parallel, like in our first example. Looks like it's the same length, but they are going in opposite directions. Vector v has its initial point up here, pointed down. Vector w has its initial point down here, pointed up. So they have the same magnitude, but opposite directions. In this case, they have the same direction, different magnitudes. Some operations that we can do with vectors, addition and subtraction, is what we're going to take a look at here in this video. We can also look at scalar multiplication, dot product, and cross product. Okay, so looking at vector addition. If we say the sum of vector A plus vector B, well, we're saying that that's the vector from the beginning of vector A to the end of vector B. So we place the tail of vector B at the head of vector A. So remember that we call this point here the initial point of vector A, or the tail. And where the arrow is, that's our terminal point. We call that the head of vector A. So if it's A plus B, then we're going to take vector A and add vector B to the end of it. So we're going to take vector A here, and then we take vector B and just add it to the end. Okay. Now this here, this image that we see here, does not represent vector A plus B. When we've got addition here, we're going to call that the resultant vector. This just represents these two vectors put together. So we have to create the resultant vector. Let's go red here. So that's going to be this vector right here. So this vector in this direction from the tail of vector A to the head of vector B is going to be vector A plus B. So now we have a new angle with this vector and a new magnitude. We can't just simply take magnitude or direction from A and B and combine them. It gives us a completely new vector. Now looking at subtraction, there's just one difference we have to put in here. So vector A minus vector B is really the same as vector A plus negative vector B. So we still can think of it, since it's addition here, as taking A and adding vector B to it, but this vector now has a negative on it. So what that's going to do is that's going to take vector B and it's going to flip it around and go the opposite direction. If we think about these two vectors here, they're going opposite directions, and vector V is basically a negative, or it's equal to negative vector W, because it's the same magnitude, just opposite direction. So we have to take this vector B and we have to flip it. So let's simulate or copy vector B here. We're going to take this here, but now we're going to have to flip it and go the opposite direction. So this new vector in red would represent vector negative B. And now we've got our resultant vector that's going to go from here to here. And again, this is the start of the two vectors we've combined. So this is also the start or tail of our resultant vector. So we'll put that in, let's go blue. So our resultant vector goes from here to here. Remember, that's going to be very different than if we started here and went in this direction. So our blue vector there is going to represent vector A minus vector B. Now, these two are not going to be equal to each other. If we were to take, or say, vector B minus vector A, well, then we're taking vector B here, and then we're adding this vector A to the end of it, but flipping it so that it now goes in this direction. So it creates a very similar resultant vector, but it's going to be in the opposite direction because we would be starting here and going over and down, whereas for A minus B, we're going up and then back here.